Just remember, before I forget, that after this talk we have our alternative lectures for the next term. Pretty much every position is open to people if you're a member of the society. So if you stay along for that, if you want to be part of the society in the coming terms. Also, we'll be filming the talk and everything online, so if you don't want to be in the camera, then avoid this space here. But on to the speaker, we're very lucky this week to have Professor Sir Meurig Thomas from Cambridge, having completed his PhD in Wales, living at Queen Mary, and being former head of physical chemistry at Cambridge, the Royal Institution, and master at Peterhouse College. He's also won the Faraday Prize twice, and obviously it was 1991 for his contribution towards science populism. It's one of our most distinguished speakers we've had for a long time, so I hope you'll give him a warm welcome and appreciate the talk.
Well, Mr. Chairman, ladies and gentlemen, thank you very much for inviting me. It's a pleasure being here. I've lectured in this theatre at least 20 times, partly because of invitations from Professor Edwards. Now, my thesis this evening is a very simple one. It is this. It comes in three parts. That expert scientists and technologists are not necessarily the most accurate compared with younger colleagues, and sometimes compared with even members of the general public, some science fiction writers, for example, in predicting the future, predicting the nature of developments, even as near as 5 or 10 years away. The second part of my thesis is that techniques and tools are far more important than ideas and concepts in driving forward the whole arena of science and technology. And thirdly, chance does certainly play often a very significant role in some quite sensational advances. Now, I'm going to begin by just reminding you of two very, very famous men. They were the sort of archdeacons, you like, of 19th century, early 20th century science, Lord Rayleigh and Lord Kelvin. Well, some of their statements they did retract. I mean, look, Lord Rayleigh is president of the Royal Society, the first recipient of the Nobel Prize in Britain. I've not the smallest molecule of faith in aerial navigation other than ballooning. And Kelvin made a similar remark. Kelvin even disputed that X-rays existed. He thought it was a hoax. Now, this gentleman could certainly be forgiven for the statement that he made. It must have been inconceivable more than a century ago that humans could, as it were, non-invasively approach how the brain works. The cartography of the human brain can now be explored, as I shall say. I'll show you in a few minutes. Von Neumann in 1956, it was 3 years after the so-called Zeta experiment. Now, there are members of this audience who've never heard of the Zeta experiment, but some have. I mean, I was a student at the time. In Harwell, the Zeta experiment was sensational. 1953. It was demonstrated, in inverted commas, that warm, hot fusion was a reality. And that's what prompted people like von Neumann to predict that, energy in future would be so readily available. Now, in South Africa, for example, where they produce most of the platinum, they have to ration the energy at the moment because there's not enough to go around. And you know the public debates in every country in the world. How do we manage to sustain civilized life with enough energy? In 1933, in New York City, Lord Rutherford, president of the Royal Society, Cavendish professor in Cambridge, Nobel laureate, described the work that he had done to win the Nobel Prize. And one of the statements that he made was this: Anyone who thinks that you can derive energy from nuclear reactions is talking moonshine. Just imagine, right? He was, what, something like 62 years of age. A 40-year-old, brilliant Italian-American, Enrico Fermi, less than 9 years later, had not only designed, built, and operated the nuclear reactor in the University of Chicago. So that's a very nice illustration. But there are many other examples. Look, the Scientific American, in 1920, I wasn't alive then, but I do read the literature, they had a huge series of editorials from their main editor and sub-editor. And it was predicting the future on the basis of the last 75 years. In 1920, it had been going for 75 years. And look what they said, amongst other things. Aerial travel will be divided between two types. The dirigible being used for long distances and transoceanic travel, while the airplane will be a standard machine on overland routes, where the distance between stops is shorter. Experimental work, this is what I like, which is being carried out in producing a steam drive for airplane service that was going on at MIT at the time, has given such promising result that it is quite possible a combined steam boiler and steam turbine, admirably adapted for larger machines, will be in extensive use within the next 5 years. It's laughable, isn't it? And you know, a 26-year-old flying officer from the Royal Air Force won a scholarship to come to Cambridge, in fact to Peterhouse as a matter of fact, and was already in the early 30s talking about the jet engine, which he effectively invented. Here he is, Frank Whittle, giving the Christmas lectures in the Royal Institution on petroleum. Now, I could give you another lecture entirely on petroleum. Pretty well everything in this room, everything that I'm wearing and that you're wearing, and most of the things that you need in civilized life, from toothbrushes to margarine to all sorts of medicines, etc., are made from petroleum, usually by catalysis. What he demonstrated that day was this lady, everything that she wore came from petroleum, right? But here are some of the jet engines that he invented. In fact, you know, the National Academy of Sciences and the Committee on Gas Turbines in 1940 stated, in its present state, and even considering the improvements possible when adapting the higher temperatures proposed for the immediate future, the gas turbine engine could hardly be considered a feasible application to airplanes, mainly because of the difficulty in complying with the stringent weight requirements imposed by aeronautics. The present internal combustion engine used in airplanes weighs about that for horsepower, and to approach such a figure with a gas turbine seems beyond the realm of possibility with existing material. And Frank Whittle has written, "Good thing I was too stupid to know this," right? You know, there were the experts, and here was this young man, an engineer who was obsessed with the idea that you could go back to Hero of Alexandria in ancient Egypt and in the great Greek fluorescence in Alexandria, where Hero demonstrated the principle of the jet. Now, there are many other things. Let me just build into this next tabulation. In 1937, one of the most enlightened presidents that the United States ever had, Franklin D. Roosevelt, set up a committee of the good and the great, businessmen, engineers, technologists, mathematicians, biologists, agricultural experts, chemists, biochemists, etc. He instructed them to report within 5 years or less, to tell him what was going to be the likely developments in science and technology on a timescale of about 20 years. Because by knowing such things, he could better lead the nation. Very enlightened view of what he could do. Now, that report was duly published. Here it is. Well, no, it isn't here. I don't want to show you that report. In fact, I don't have a copy, but I've seen very detailed records of what they did identify. They pointed out, for example, that you could readily make gasoline, petroleum, petrol, from coal. Well, there was nothing big in that, because the Germans in Fischer and Tropsch in 1920 had demonstrated that. They did emphasize the extreme importance of agricultural work and agricultural science, agricultural chemistry in particular, in order to feed the United States. Of course, ammonia had been discovered by then, that is to say, manufacturing ammonia from gaseous nitrogen had been invented, so that they highlighted that. But now I've taken the liberty of extrapolating beyond 10 years, because I tell you why. In 1982 to 86, I sat on a cabinet office committee, and one of the jobs we were given to do under the chairmanship of the then Director of Research of Imperial Chemical Industries, about 20 of us, including Rex Richards, by the way, Vice Chancellor of this university formerly, promising areas of science. We had to identify and write a report for the British cabinet. Well, let me tell you, what we did predict that really did come to fruition was magnetic resonance imaging and confocal microscopy. I wanted to include the fuel cell, but I couldn't convince anyone else. There were 13 of us in all. No, they said, you know, the fuel cell, it's not likely to be of any importance. Well, look, here's what President Roosevelt's commission missed. Now, you can forgive them for not being able to identify a totally new discovery like nuclear fission or fusion, or, well, even the laser, although a perspicacious physicist would say in 1917, Einstein worked out the Einstein coefficients between various energy levels, and you could have, if you were smart, really smart, something like Feynman, for example, you could have predicted that a laser could one day be built. But leaving that aside, the transistor, computers, laser discs, synchrotron radiation, well, that could have been predicted. Jet aircraft, rocketry, stereoregular polymers, natural gas, fax machine. Do you know when the fax machine was first invented? I remember asking this question in Cambridge, and the professor of English, she said, 1920. I said, no, Gillian, you're wrong. It was 1841 by a Scottish watchmaker. And in 1842, Caselli, an Italian physicist of Florentine extraction, did it independently. 1841. Well, her reply was, well, in those days, there were 7 postal deliveries in London per day. You didn't need a fax machine, right? But that's the fact. The fuel cell, 1840. The first paper was by W.R. Grove, my fellow countryman, in 1838. It's all the rage now. I mean, not just for vehicles and transport and so forth, but for community centers, hospitals, and methods of generating local energy with available biomass or whatever. The charge couple device. Tomography. Now, here again, you see, a physicist, mathematical physicist in the University of Leipzig, again in 1917, worked out the mathematics of tomography with no particular application in mind, but he described what it all entailed, taking 3-dimensional images from a series of 2-dimensional projected images and recombining them. Charge couple device. Now, that, I think, has been one of the most sensational of devices. I gave this lecture in Göttingen about 10 years ago. Afterwards, the man in the front said, you know, I shared an office in Bell Labs with Bill Boyle. Boyle was the man who, only 2 years ago, just before he died, won the Nobel Prize with his friend, George Smith, for inventing the CCD. And what this German told me was, nobody in the Bell Labs thought that it was a major discovery. They didn't open a bottle of champagne. And yet, when you think of what it has done to astronomy, to endoscopy, to medicine, to marine biology, you know, there's a census, David Attenborough's pictures of underwater life. All of it becomes almost possible because of the existence of the CCD and all the camcorders and all the mobile phones and so forth from which you take photographs. Oh, to that. Google has only been going for 12 years. Can you imagine a life without Google now? You know, I mean, who would have predicted that? Well, in 1936, apparently, H.G. Wells, lecturing in the Royal Institution, did say, scrap the idea of Encyclopedia Britannica, Encyclopedia Americana, Encyclopedia Judaica. Just let us have an international encyclopedia, not biased by any country. And of course, that's what you got in Wikipedia. Of course, we now realize that Wikipedia, especially in China and so on, and many other places, they've now been plagiarizing and producing things that somebody in this room may have written, that I may have written, and you know, they've got it in their database. Now, looking at the biological world, certainly they should have picked up antibiotics. After all, you know, the discovery of penicillin was a long time by Fleming. Immunosuppressive drugs, well, again, you know, it's in the sewers of Naples, apparently, that cephalosporin. Now, E.P. Abrams of Queen's College in this university was the man who really spotted the importance of these immunosuppressive drugs. All spare part surgery, you know, having a new liver, a new heart, suppressing rejection of organs, is all dependent on these drugs. Transplantation medicine, the structure of DNA. I mean, nobody was really looking for that. It was Jim Watson's obsession when he came to Cambridge to convince people like Perutz and Kendrew, who were obsessed with proteins. They didn't think that nucleic acids were all that important. And then, of course, as you know, well, all heredity and various other mysteries hitherto have been more or less resolved. Protein engineering has become a feasibility. Genetic fingerprinting. You couldn't have predicted that you were going to do that. It was an accident in the University of Leicester by Jeffries, Oxford graduate. Nobody set about saying, look, and this is a very important message to the funders of science and the policymakers and the politicians. What you discover is a chance. It's something unexpected. You have peripheral vision and smart enough to understand it, and so on. Now, the flexible endoscope, I'll tell you the story a little bit later of how that came brilliantly into existence in London as a result of a chamber music practice. And I'll tell you, well, this man Starzl, whom I've met, he's a quarter Irish and quarter Czech and half American. He has carried out more liver transplants than all other liver transplant surgeons in the world. I mean, it's difficult to believe it, but you know, he's now 88 years of age and he's pretty nimble. He's no longer operating. But he would do something like 500 liver transplants in Colorado and then later in Pittsburgh per year. That means 2 a day. Because one of these, you know, some surgeons like Debicki, you know, they work 18 hours a day, they have a big team and so forth. Well, I heard him give this talk based on that article and how, you know, without the drugs, none of this would have been possible. Now, I'm not going to say too much about functional MRI, but, you know, you remember Sir John Ericsson's quip, the Surgeon General to the Queen? You can actually tell a person to imagine that he or she is playing tennis, and you can activate that same part in the brain that is actually activated when he is playing tennis. That's what this paper It appeared in, I think it was Science, it is Science, yes, about 6 years ago. Now, this is one of my favorite pictures, actually. The chemical cartography of the brain, right? How do you look inside the brain? Well, you have fluorine 18 is one of them, and carbon 11 is another. You have to have a synchrotron to be able to manufacture this, because their half-lives are very short. But what kind of half-life are we talking about? What kind of radioactivity? It's positron emission. Now just think of the story. Paul Dirac was an engineer who graduated in Bristol, but he felt more inclined towards mathematics and quantum mechanics. He was born in 1902. He came to Cambridge. He was clearly a phenomenally gifted mathematician, physicist. And in 1925, 26, 27, especially 27, following the work of Schrödinger, Born, Pascual Jordan, and Heisenberg, he decided that he would try and make the Schrödinger equation more complete and put in relativistic terms into it, which he did. In the process, he discovered the first ever indication that there was antimatter, the positron. Well, it was regarded as a novelty for quite some time. Even the physicists thought, well, you know, fine. If they exist, they exist. According to pure theoretical physics predicted that. Not many examples in theoretical physics or theoretical chemistry which tells you that something is going to exist, and it really does. 4 years later in Caltech, this man, Carl Anderson, identifies the positron. Well, by that time, he had won the Nobel Prize, and he won it a few years later. Now, every major hospital in the world now uses positron emission tomography to look at the brain and other parts, non-invasive examination. It's an incredible story. Now, that would have been very, very difficult for that committee by Roosevelt to have set up. Here's the famous letter sent from the London institution, which now no longer exists. It's the London School of Oriental and African Studies now, but this man, W.R. Grove, who was a lawyer, graduate of Brasenose at Oxford, but fanatically keen on electrochemistry, he writes to Michael Faraday, "I've just completed a curious voltaic pile, which I think you would like to see. It is composed of alternate tubes of oxygen and hydrogen, through each of which passes platinum foil, so as to dip into separate vessels of water acidulated with sulfuric acid, the liquid just touching the extremities of the foil, as in the rough figure here." And now he puts, you know, a galvanometer or voltmeter on these extreme electrodes, and he generates 1.5 volts. That's the combination of hydrogen and oxygen silently to combust, to give you energy, a source of energy, chemical energy, not by explosion of hydrogen and oxygen, but electrochemically. Now, at this point, I thought I should stand back a little and say, you know, I could give you numerous examples, but there has to be a kind of structure to the way in which one foresees or interprets how the evolution of science and technology has gone on. There are external factors, political, societal, commercial, military. There are internal factors, tools and techniques. Just imagine, you know, Galileo with his telescope, and Aston with his mass spectrometer, and Archer Martin with his chromatograph. Instruments, machines, and methods. Pervasive influence. There are incredibly gifted people. Newton, Maxwell, Einstein, Darwin. Fisher you might find strange, but he was a wonderful statistician who made perfect sense of agricultural produce and interpreted it in quantitative ways. All these names, there are others. We talked about some of them today, Landau, when we were in Queens for tea. And also the right place and the right time. Now, let me just tell you first of all, an example of a political decision. The Medical Research Council was founded in 1911. It was a consequence of what the Chancellor of the Exchequer of the day, David Lloyd George, in his famous budget speech, in which he introduced the national health, well, not the national health that Aaron Bevan introduced, but it was the national insurance concept, the question of looking after people. If you felt that young people had to go to war to fight for their country, you should also feel that you should look after them and protect their health. Not just they themselves, but their families, their children, their parents. And consequently, the Medical Research Council was set up by David Lloyd George with the intention of doing preclinical medical research. And when the war ended, when it became apparent that there was gangrene and various other diseases that were dreadful, tuberculosis, for example, was endemic. The Medical Research Council was given even further powers, and at that time, Lloyd George became president. Well, now the MRC has produced incredible success. I mean, the Laboratory of Molecular Biology alone in Cambridge, which is an MRC offshoot, has produced 15 Nobel Prize winners, monoclonal antibodies, various kind of, Fred Sanger, 2 Nobel Prizes, insulin structure, the sequencing of the DNA, structure of DNA, and so on, protein engineering. So that's a political decision. Societal, well, the best example I have of societal is one in which is going to involve Count Rumford of the Holy Roman Empire, who was an American named Benjamin Thompson, born in New England. He was on the side of the British in the War of Independence, by the way. He was knighted by King George. He came to Britain, and he founded the Royal Institution, incidentally. But before that, he went to Bavaria. He was a man after money, and he was an extremely egocentric, somewhat arrogant individual, but a brilliant man. And Karl Theodor III in Munich was troubled by the fact that there were so many beggars and vagabonds on the streets of Munich. It was the worst city in Europe, that he wanted them cleared. And the bargain that Benjamin Thompson made with him was, look, you make me the Supremo, I'll be your general, I'll be in effect your prime minister, if you wish, in Bavaria. I'll run your army, and I'll deal with these people. In fact, in 1790, on January the 1st, he sent in the troops to the streets. He rounded up all the beggars, their family, their children, and put them in what would otherwise be called a workhouse, but it were called houses of industry. And he got them to make food, like Rumford soup, which is based on potatoes. He got them to drink coffee rather than alcohol, because coffee was safe. He clothed them, he fed them, he gave them good lighting. I'll show you a few examples. He did some extremely important practical science, practical physics. He invented the coffee drip feeder. He invented double glazing. He invented pressure cooking. So many other things. Now, military and commercial. Well, commercial, I mean, if there's an opportunity, if you sell cameras and so on, if you sell phones, etc., this goes without saying. But the military, after Sputnik 1 went up, President Eisenhower called in, he was the first American president to appoint a chief scientific advisor. He said, look, we're not going to be surprised by the Russians anymore. We've got to do something, especially if they're equipped with intercontinental missiles. We need early warning systems. You've got to do something. I'm not speaking to the generals, I'm speaking to you as scientists. And the scientists very quickly got together and set up ARPANET, which is the precursor of the World Wide Web and the Internet. And there were just 4 nodes in Santa Barbara, in Santa Cruz, in UCLA, etc. And all these sort of major mainframe computers were connected. And this was something that was felt to be important, because then you could disseminate the areas where you could have a response to an imminent attack, a military attack. It wasn't one particular nerve center. It was distributed. Well, within a few years, from 4 it went to 11, 117, and then a few years later it was in thousands and then millions, right? And that's the origin. Of course, there's other stories which I can tell you about, CERN, etc. But that's an example. Now, the pervasive influence I've touched upon, but now let me go. Here's Count Rumford. He was made a count, by the way, because the Karl Theodor was temporarily in charge of the Holy Roman Empire in an interregnum period, and he had it within his gift to make this man a count of the Holy Roman Empire. But he was Sir Benjamin Franklin, and when, after solving what he thought were the problems in Bavaria, he came to London in 1798 as Karl Theodor's ambassador to St. James. When he attempted to present his papers to King George said, well, I've already knighted you. You are Sir Benjamin Thompson. I can't accept you as a foreign secretary of a foreign nation, so go and do something else. And that's when he founded the Royal Institution of Great Britain, 1799. Anyway, this is a portrait that hangs in Harvard. There's a Rumford professorship in Harvard. There's a Rumford Prize in the US National Academy. There's a Rumford Prize in the Royal Society. This man was a pretty brilliant individual. You know of the story of how he demonstrated that caloric was not a liquid, that you generate an indeterminate amount of heat by friction. And he saw that through the boring of cannons and so forth. Here are some of his achievements as an inventor: the kitchen range, convection oven, lustre pots, the photometer. He wanted good lighting for those people who had been impoverished and who were begging. And he devised a photometer, and he in fact introduced the notion of candle power. And candle power was used by physicists. Mike, I'm sure you were brought up on it, I was. And it lasted for about 170 years, long before the age of SI units and so on. And a special thermometer to measure body heat. And you see, as an inventor, he demonstrated the nature of heat, measurement of heats of combustion of fuels. He wanted to run the place efficiently. Development of techniques of measuring radiation, determination of gunpowder and contribution to ballistics. He was a pretty good mathematician. Measurement of specific heats. He discovered convection currents in liquids. Measured thermal conductivity of many gases and heat losses by radiation from surfaces. Look at all those. Just one man. Very, very percipient individual, but it was societal pressure that gave rise to that. Now, why do I show you this? It's the European Journal of Physics, Physical Journal, way back in 1999. There are something like 400 authors in this paper from 157 different institutes from all over the world. Here they are. Now, this work was done in CERN. It was absolutely essential when you carry out experiments of a physical kind which requires such military precision, such preparation, such interrogation, such discussion. You've got to be in touch with all these different establishments. And that's when Robert Kalilew and Tim Berners-Lee, the founders of the World Wide Web, got at it and produced hypertext and various other methods of communication. Now, the consequence of this, 2 years ago, one of my friends in Peterhouse showed me the Atlas collaboration from CERN. There are 8,000 co-authors on this paper. Now, you know, I wouldn't want to work in a team where I have 7,999 collaborators. I don't think I would meet them. Anyway, I thought I would show you the curve on how the World Wide Web took off. It's not exponential, it's much sharper. It's x to the x, look at it. And I only went as far as 1996, right? But here are the two people who were the largely responsible for the invention. Now, chance discoveries. I'm not going to go through every one of these. I'm just going to take 2 or 3. Well, I've mentioned Jeffries already on genetic fingerprinting. It's a very important thing, not just in legal cases and in crime detection, but in the migration of mammals and animals and humans from one continent to the other. You can do this through being able to genetically fingerprint. Lithium medication, you know, this man, this doctor from Australia, from Melbourne, he was preoccupied with the conviction that when people were manic depressive, the real cause of it was the metabolism of uric acid in the body. He was so convinced of this that he started doing experiments in his hospital and on himself, and he looked around and he realized quickly that uric acid itself is insoluble. So you have to take the salts of uric acid and feed them. And lo and behold, he discovered that lithium urate, which is very soluble, was extremely good. It was giving tremendous results. So he thought one day, well, do I need uric acid? Why don't I try lithium carbonate? It is cheaper. And it's available. It occurs as a mineral, actually. And this is what he did. And it was even better. Now, lithium therapy, my sister, who is now dead, she lived for 15 years on lithium medication. And it transformed her life because she was a manic depressive at one stage. And lithium therapy worked with her. Now, that's an example. Now, it took about 25 years before the pharmaceutical companies could manufacture this because they made very little money out of lithium carbonate. You can't patent it for a start. You see, normally, I mean, you can understand, you know, there are certain very rare diseases which can be cured, but if you're going to cure them, you need extremely careful scientific research and development. And then, in a justified way, the people who spend that money must recover it in some way. So, you know, that's the balance. Now, radio astronomy. Jansky graduated from Harvard. He joined the Bell Labs. The job that he was given in the first week that he was there in New Jersey, look, try and make sense of the crackle that you hear in a radio set. The wireless, as we called it, it crackles. What the heck is the cause of that? Try and get rid of it. Within a few weeks, he realized that it has nothing to do with the circuit. It has everything to do with cosmic rays. You know, he went to his garden and then he established it. You can see how he could have done that, right? It was cosmic ray interference that gave rise to the crackle. That's how radio astronomy really took off with that observation. Now, cisplatin, Rosenberg, whom I knew very well, one of my best ever postdocs, went and worked with him at Michigan State University. Rosenberg was from New York, very smart physicist in NYU. And he said, I'm giving up physics. I'm going to turn to biology. I can do biology better than some biologists, I'm sure. I mean, there are some things that biologists don't even think of, and I as a physicist can think of them. And one of the first things I'm going to do is I'm going to apply an electric field and see what influence it has on cell division. Whether a cell of whatever, Escherichia coli or whatever you put in, how rapidly or how slowly or how differently does it undergo meiosis and mitosis. And I put 2 platinum electrodes into this solution, and lo and behold, he sees a dramatic effect. And he thinks, well, that's it. See, I told you. You know, you need a smart physicist. But what he realized was, because he had, in fact, one of, Alan, you know Andy Thompson, one of your friends. He worked with Bob Williams. Andy Thompson and my postdoc, John Williams, were with Barney Rosenberg on this occasion. And it was Andy Thompson who said, why not check whether that platinum is dissolved? And indeed it is. And it forms a square planar complex, dichloro diamino platinum. And that's what slides in between the base pairs in the DNA. And that's the cause of the cure of cancer, which is now available on the market. It gets rid of testicular cancer and often cervical cancer, but not completely. And that's a discovery. Now, I don't have time, except maybe I should mention this man, Ridley. Yeah, I've got to, because I've got this man here. Ridley didn't get his Fellowship of the Royal Society till he was about 82. He was a medical doctor in the Second World War. And he spotted that this man, who was an extremely courageous pilot, a mouse cleaver he was called, he fought in jet planes, well, not jet planes, but in fighter planes, flying over the British Channel into France, coming back, being shot down. In fact, he was recovering from having come out from a plane which had been hit by a German shell, and the cockpit was plastic, polymethyl methacrylate, right? And some of it went into his eye, and it shattered the retina in the other eye, so one eye was completely lost for vision. Now, Ridley was his doctor, and Ridley spotted that Cleaver's eye could tolerate polymethyl methacrylate indefinitely. There was a fragment or two of it in the eye that did no damage. So Ridley thought, well, you know, this is a tremendous godsend. I'm going to make intraocular lenses for people who suffer from, you know, eyesight trouble and have a corneal replacement. And now something like 100 million such replacements occur in the world every year. And it was this man who started it. And he did it off his own bat in St. Thomas Hospital in London. And in fact, the medical profession were very dubious. They even ostracized him. But he proved his point. And he's the Ridley who was the descendant of the Ridley who was burnt at the stake, by the way, for religious conviction. I won't talk about these two physiologists, but I want to now show you this picture, which you've seen. It's the hand of the wife of Röntgen. Röntgen had two interests as a physicist. He was interested in phosphorescence, either as fluorescence or luminescence generally. He was also interested in the discharge of gases through evacuated tubes, a kind of work that Faraday and later Crookes had done. Now, on November the 8th, after he'd finished teaching, it was a Friday, in Würzburg in Bavaria, he was in his lab. It was about 5 o'clock. And on the benches in the lab were some platinum phthalocyanine and barium phthalocyanine and various other highly fluorescent material. They're well known. They'd been known to be fluorescent for tens of years before then. And he wanted to investigate the lifetime of this fluorescence and so forth. Well, he was about 10 or so yards away, passing 2,000 volts through this cylindrical tube with 2 electrodes, and he noticed, it was a darkened room, that there was fluorescence. And he stopped passing the voltage, and that stopped. So he obviously discovered something. So he put a sheet of paper. It continued. He put a piece of wood and cardboard. It continued. And then there was a piece of wood which had white lead paint on it, and it stopped. And that was the discovery of X-rays. You know, the first ever Nobel Prize winner, Röntgen. Within weeks, there were people in Massachusetts and in Moscow feeding bismuth to mice and rats and rabbits and monitoring using X-rays of the kind that Röntgen had discovered. They didn't know what they were, of course. I mean, some people thought they were corpuscular, like alpha particles, and some people thought they were waves, like ordinary light. It's another story. But that is one of the sensational things. And of course, radioactivity was discovered as a result of an experimenter in France trying to repeat and proving that the sun's light could activate a particular solid and make it to emit X-rays. And he put photographic paper around it. And indeed, there was some emission, but it was because he'd used uranyl salts, and it was radioactivity. Now, there was this enterprising Frenchman in 1897. Look, if you've gone through any airport in the world these days, you get X-rays looking at your luggage. This man was a pretty smart businessman. 1897. Now, here's the prince of them all. There's a wonderful paper that he wrote in the Royal Astronomical Society of Canada. If you ever go into the library and see the complete works of Rutherford, you should, and every single paper is worth reading. He completely settles the issue. He is one of the great physicists. Now, what he did in this paper, which he published from Montreal, from McGill University, Montreal. And let me tell you, first of all, he graduated, well, he was from New Zealand. He came on an 1851 exhibition to Cambridge. He worked with J.J. Thomson. He got his PhD there. And shortly afterwards, he applied for the chair in Montreal. And he was, what, 26 or something when he got it. Now, 3 things, a concatenation of fortunate circumstances. 3 things happened which really were so perfect for him. Number 1, there was a very rich Scottish immigrant who was in Montreal, who was giving loads of money to the university to make the physics department there, if anything, better equipped than any physics department in the world. And he was trying to compete with Cambridge. So the amount of materials and equipment that you could have in the stores, Rutherford could sign out 2 grams of radium bromide. It's inconceivable. Radium bromide was in the stores, right? Now, there were 2 out of 3 things. This man, so William MacDonald, had given some money to Montreal, to the university. There was radium in abundance. And the other piece of luck was there was an Englishman named Frederick Soddy, who had studied in Aberystwyth for a year, and who came to Oxford and took his degree, his bachelor degree in chemistry, from Merton College. And as a 22-year-old, he bumped into Rutherford, and they struck up an immediate friendship. They got on like a house on fire, and it so happened, if you read in retrospect, Soddy was an absolutely brilliant experimentalist. He later became, Peter Edwards' his predecessor, professor of inorganic chemistry in Cambridge, in Oxford. He was the one who invented the term isotope. But the dexterity with which these people studied radium and polonium and other radioactive materials that Madame Curie had discovered and worked with, in pitch blende and so forth, they propounded a theory of radioactive decomposition which was so iconoclastic. Young people, 22, 23-year-old and 27-year-old. And many people disputed the reality of it. I mean, even Lord Kelvin, who was the great panjandrum of British science, disputed it. And this paper, what he did in this paper was to take about 20 minerals, some from Devon, some from Sri Lanka, some from Russia, some from Argentina, some from Canada, some from Wales, all over the place, all of them radioactive. And he measured the half-life. Well, he measured how old those minerals had to be. You see, he worked out that knowing the half-life, which he had carried out many measurements of, knowing how much helium was being produced, you could work out the age of these minerals. And he was coming out with figures like 800 million years. Now, Lord Kelvin, who was a brilliant physicist, had said that the age of the world was no more than 40 million years. And how had he come to that conclusion? Well, he said, look, the Earth was formed as a hot, molten globule. Now, by the inexorable laws of physics, it loses heat, it radiates, and it cools. If you measure the surface temperature of the Earth now, and guess what it was to begin with, you can deduce how old the Earth is. And he predicted it was 40 million years. Now, I have to tell you, Rutherford was asked to give a Friday evening discourse in the Royal Institution in 1904 when he came to receive his Beckerian lectureship. Now, I've got to find this little sheet for you, because those of you like Mike who lectured at the Royal Institution know that when you go in, it's half dark. I came into the room, this is what Rutherford said in writing to his wife in New Zealand, which was half dark. And presently I spotted Lord Kelvin in the audience and realized that I was in for trouble at the last part of my speech dealing with the age of the Earth, where my views conflicted with his. To my relief, Kelvin fell fast asleep. But as I came to the important part, I saw the old bird sit up, open an eye, and cock a baleful glance at me. Then a sudden inspiration came, and I said, Lord Kelvin has limited the age of the Earth, provided no new source of heat was discovered. That prophetic utterance, ladies and gentlemen, referred to what we are now considering tonight, radium. Behold, the old boy beamed at me, right? So it's a lovely story. And he writes to his wife and tells him that. Now, that was the really great. That's it. He comes in, here's Kelvin. And, well, this is James Dewar. If you want to know who these are, they're wonderful. You know, this is Sir Oliver Lodge. This is Ludwig Mond, one of my great heroes, one of the greatest industrial chemists of all time. A man who set up the Davy Faraday Research Laboratory. Extremely rich man. He gave 58 of his old masters to the National Gallery. I could give you a whole lecture on him. This is George Matty of Johnson Matty fame. This is Lord Rayleigh. This is Sir James Creighton Brown, the Queen's physician. Sir William Crookes. A.J. Balfour, the Prime Minister. This is Stokes. This is Lord Rister. This is Kelvin. And here's a young Italian, a future Nobel Prize winner, Marconi. So that's quite a dramatic event. Now, you know, after that discourse, Rayleigh went up to Kelvin and said, I'm sure you will have to give in that you're wrong about the age of the Earth. I'll wager you something like 5 shillings. You know, these are very rich men, but 5 shillings was something. And what I'll do, I'll arrange an evening in my baronial home. You know, Lord Rayleigh was to the manor born. If you go to Tarling in Essex, he did half his experiments there, and the other half in the Royal Institution, some in Cambridge. And he arranged, he said, he told Kelvin that he would bring both Rutherford and he together. And in fact, I know the present Lord Rayleigh, who was the great-grandson of Lord Rayleigh, and when I went there about 2 years ago, I said, can you let me see the visitor's book for 1904? And at Tarling Place, Lord Rayleigh's home, right, where he conducted, there were frequented Wardian weekend parties. One of these in May, that Rayleigh brought the young Rutherford in there. And here's the visitor's book, you see. Now, Mike, you would know some of these really great people. Arthur Schuster, right? Fantastic man. And here's his wife, you see. And this is Kelvin. And Rutherford is here somewhere. Oh, yes, there he is, okay. And that's it. That's the night. And indeed, he did give in and he paid up on the bet. So that's it. Now, look, here is an example not of an accident, but of premeditated experiment. This man, Lowy, said, I'm beginning to feel that X-rays are waves. And if they're waves, then there should be diffraction. Well, the rest is history. You know, that was done in 1912, the centenary last year in Munich. And this 22-year-old, when he read about it, said, well, I have an easy way of describing what diffraction is. I can regard it as being partial reflection. And if you get incoming X-rays and you've got rows of atoms in a solid, and then you reflect partially, then you can set up an interference condition. And that's how we derived n lambda equals 2d sine theta. And look, all of this now, within years, well, in the lifetime of Lawrence Bragg, he transformed mineralogy, he transformed chemistry, he transformed geology, physics, metallurgy, even, well, molecular biology, because his acolytes solved the structure of proteins, of DNA, and of enzymes. David Phillips and Louise Johnson, who recently passed away, sadly, she was professor here, David Phillips professor. David Phillips was a friend of mine, a Cardiff graduate, and worked at the Royal Institution. Who would have said, you see, look, you can picture, I'm a romantic at heart. You can imagine a medieval king saying to his advisor, what's the secret of heredity? How is it that, you know, my children are somewhat similar to me? How does it work? And the perspicacious advisor would say, first of all, solve the structure of zinc blende or sodium chloride, and then gradually you will work out. You'll get to this, and you'll get to DNA. In fact, I wanted, well, here's DNA, I don't need to spend any time on it, but this is a story that many of you may not know. John Kendrew, who later became president of St. John's in Oxford, was a Cambridge man. He was a close friend of mine, and he was a Peterhouse fellow. He and Max Perutz were working together. They founded the molecular biology laboratory. One night in early March of 1953, Erwin Chargaff, a very formidable and somewhat ostentatious Austro-Hungarian professor of biochemistry in Columbia University and who was a friend of John Kendrew, came to dinner in Peterhouse. This is the high table in Peterhouse. This is Kelvin there, by the way, because he was a Peterhouse student as well. That night, Kendrew had brought in two of his acolytes, Jim Watson and also Crick, who still hadn't done his PhD. And Chargaff said to these two butterflies, as he called them, "What are you working on?" And they said, "DNA." "Have you read my paper in DNA, on DNA? Where did you publish it?" "In the Swiss journal Experientia." "Never heard of the journal. What does it say?" I found out something quite important, I think. I showed that whatever the source of the DNA, the ratio of guanine to adenine and cytosine to thymine is always 1:1. Now they put down their knives and forks and they didn't wait for the dessert course, because this was the clue they really wanted. They had built the double helix, but the base pairs were not fitting. So when you had that secret, cytosine, guanine, adenine, thymine, they were able to put it together. And within less than a month, they solved the structure. Now, it would have happened anyway, whether that event occurred or not. But Max Perutz always used to tell that story, and John Kendrew confirmed that it's true. Well, this is how lysozyme works, that again. X-ray crystallography is what demonstrated that. The charge couple device, here it is. Look, Polaroid lens went out of business. You don't need any silver bromide or silver halide for photographic plates. The CCD is 1,000 times as sensitive as the most sensitive photographic plate or film that you ever have. If you're an astronomer and you're using data from the Hubble Space Telescope, here are the sort of moons of Jupiter, you can find out all sorts of incredible things, that there are volcanoes on some of these moons, for example. Look at this wonderful galaxy, which is a sort of 1,000 light years in height. Over a period of 10 days, I'm talking about an experiment of 10 years ago, in a spot no more than that, in solid image, right? I mean, solid angle. It's the diameter of that. They focused using the camera on the Hubble Space Telescope. And you could see galaxies in various states of evolution. As a result of the CCD and the Space Telescope, we now, at this time, think that the size of the universe is at least 1,000 times as large as we thought it was 20 years ago. And in fact, there is still a debate. I can't understand it, Is the universe limitless? Is it unending? This is where you get into the realm of cosmology that I don't understand. Now, the last thing I'm going to talk about is the endoscope. Schindler was a Frankfurt surgeon, and he developed the rigid endoscope. Now, you had to be either a former sword swallower to be a good patient in order to be subjected to an examination of that kind. Just think of it, a little bulb at the end of a rigid stick, and he had a mirror up here, sort of, periscope effect, and he was looking at the inside. Well, the story I alluded to earlier, this man, Harry Hopkins, who came to the Royal Institution regularly, he ended life as professor of physics at Reading, but he was a reader in Imperial College in physics. He was a very keen musician. He showed up for practice with his chamber group, and he met a man whom he'd never met before, and they started talking. And this doctor, who was an endocrinologist, said to him, "What do you do?" "I'm a physicist." Well, I quite admire physicists, but if only they did something really worthwhile. What do you mean, he said. Well, I'll tell you. And he told him about this problem. He said, well, that's so damned easy. We can have a flexible, fiber optic. We can easily put that, right? And we could put a little bulb at the end, and we could design that within weeks. He and his Hungarian student had produced this. This is an excerpt from the later in Nature. Now, endoscopy was utterly transformed. On my way here, I was reading a paper in Nature where you can now have an endoscope which is only the diameter of the human hair. And you can have a CCD camera at the end. You can even now do 3D imaging with the endoscope. And you can have endoscopes where you can carry out an operation as well, as one of my friends in Cambridge demonstrated to me. So it's a wonderful story. Now, here's the very last comment. Chance. This young apprentice, he'd been working for 7 years as a bookbinder and a bookseller, and a man delivering papers, having left school at 13. In Marylebone in London, he had a very kindly boss who gave him the liberty of reading the books that he bound, and he was an autodidact. He really loved learning about things that, why outside his ken. All he had at school was reading, writing, arithmetic. One day, a very kindly customer comes in and tells him, would you like to go and listen to the last 4 lectures to be given at the Royal Institution by arguably the greatest scientist in the European firmament, Sir Humphrey Davy. He is retiring as director. And he jumped at the opportunity. He went there, he listened attentively, he was mesmerized. He took copious notes, he rewrote them, he bound them, and he sent them off to Humphrey Davy asking for a job. And in due course, he was appointed, and that's Michael Faraday. So, here's the interview in March of 1813, overlooking Albemarle Street. Now, there are some people here who know Albemarle Street. If anybody asks you, what's the most important street in London? Don't say Buckingham Palace Road or Regent Street. Albemarle Street, you know why? Not only because the Royal Institution is there, and because Davy and Faraday and Rutherford and James Clerk Maxwell and others were professors there. All the poetry books of Lord Byron were published there. All the novels of Jane Austen by John Meurig, number 40, Albemarle Street. And the greatest book ever, possibly with the exception of the Bible and the Quran and various other religious books, The Origin of Species was published there. So Albemarle Street, where I lived for 5 years, is, in my book, the great soap. Now, Richard Feynman said, when Faraday derived his laws of electrolysis, if you look at that very carefully, what it tells you is, the only thing that matters when you deposit, say, nickel on iron or silver on copper is not the sort of size of the vessel or the electrode or whatever. It's the amount of electricity and the chemical equivalent. Now, as Feynman pointed out, this shows you that matter ultimately is electrical in nature. So he says, one of the most dramatic moments in the history of science, one of those rare moments when 2 great fields, matter and electricity, come together and are unified. And that was done by this relatively uneducated Michael Faraday, one of the greatest experimentalists and one of the greatest Englishmen, in my opinion, of all time. Well, thank you, ladies and gentlemen. I hope I haven't taken too much of your time, but thank you for your attention. Fine. certainly. Leon.
I think ideas are by far the most important process. You talk about process, but ideas are really the drivers of where you get in science. They really are. The people who have ideas, it doesn't matter what's, other people say, oh no, you can't possibly do that. We had a guy here who invented the low temperature maser. Do you remember that guy? Now Cyril Coulson was the man who pushed liquid crystal televisions at GC, who said this man should have some money, and he produced the low temperature maser. Nobody has any idea how far that's going to get. Ideas of what it's about. I was at Nokia in the 80s, and they showed me their first mobile telephone. And the engineer said to me, what do you think about this? Should we carry on with it? And that gives you an idea. They had no idea where it was going. And ideas are the most important thing in science.
Well, I agree that ideas are important, but I wouldn't put them ahead of techniques and tools, you know. I mean, we could argue about this. There are plenty of examples that you could extra add to the one that you've already forwarded. And I could also, on the question, I mean, the CCD alone, I mean, it's so pervasive, it's transformational. It's altered the way, the lifestyle. I mean, the telephone and photographs and the iPads and, you know, utterly, utterly incredible. And furthermore, James Clerk Maxwell formulates the theory of electromagnetism, but it's really the simple experiments of Michael Faraday and his lines of force demonstrating in a real way the, in inverted commas, the reality of the existence of these lines of force. It's an interesting point. We can stay till midnight talking about this, I'm sure, Leon. Thank you for your comment.
I guess one of the more difficult questions about the observation of the talk is, what do you think will be the next sort of big thing to either generally in science or in sort of your field for the next 5, 10?
Well, you know, I've now reached the stage where I'm hesitant to predict. I mean, you know, sat-nav was first proposed by Arthur Clarke, you know, who writes science fiction, right? Later, it came from the American military, right? So, no, there are very many big things that one could hope for, but I can't honestly answer your question. There are dreams, there are ideas that one would like to feel. I mean, one of the things that I would like to feel is going to be the area for huge advances, is understanding how the brain works, you know. I mean, we do know how various parts of the body work, and how medicine and surgery and acts of the physician can help. But the brain, the whole idea of memory and the way in which instant recall and that kind of thing. Now that's the area which is far removed from my own that I would like to think would be the one where there's greater productivity to come in the years ahead, but who knows?
This is maybe slightly off the subject, but I'm curious in your opinion on young scientists working in defence and military. I mean, some amazing technologies have come from the military, like penicillin and the internet, as you've pointed out, but also some, obviously, rather less pleasant things.
Very.
How do you advise people in our position to juggle that tension?
How do you, sorry?
How do you advise us to juggle the tension between the fact that working with, say, defence could produce some amazing technologies,
yeah,
but also could be...
Well, you know, look, this is a debate that many people are divided on. The great Linus Pauling, and he really was great, he's probably the greatest chemist, possibly ever, certainly of the 20th century. He refused to work on the Manhattan Project, right? He categorically refused because he was deep down a pacifist, right? Dame Kathleen Lonsdale, with whom you worked. I mean, she went to jail during the war because of her tenacious belief that you should not devise anything that kills other people, you know. Now I, in my simple-minded way and in my incompetent way in comparison with those, felt I didn't want to actively work on any weapons of destruction. But you see, you can never tell. Sometimes you make a discovery and then it's used for military purposes and it's used to kill people. And therefore, you know, you can only plead that the whole world be changed, that you try and avoid the mentality of, for example, settling disputes by war, which is the most barbaric thing to do. It's usually sending young people to their death and killing innocents. You know, it's inconceivable that we should have evolved as human beings to behave in that way. I would, in my simple-minded way, think that you should try and avoid, wherever you can, working on things that are obviously, you know, would you spend your time working on more powerful nerve gases? I wouldn't myself, but somebody will, you see. So it's an open question. I'm glad you asked it, but I can't give you a satisfactory answer.
Thank you.
I wonder if you've ever had the opportunity to give this lecture to politicians.
You know, you're not the first person to tell. I've written a version of this up many times. And indeed, no, but the politicians don't listen anyway. Some of them do. I must say, the first time I gave this was as a Friday evening discourse in 1999. I'm beginning to feel a fraud now, you know. I'm giving updated versions of it. But, what's her name? Shirley Williams. I sent her a draft of some of the things I wanted to say, and she was quite interested in it, but most people don't. No, and indeed, you know, the policymakers, they have to really understand. I mean, the worry I have, and there are people in this room who know why I'm saying this, you know, more and more in Britain at the moment, the government, not particularly this government, but we've got into this situation, you know, isn't it an anomaly that the Minister for Higher Education belongs to the business and innovation sector of government? Business, right? Now, I'm all for business, you know, I mean, it's sensible. I believe in a mixed economy. But the universities are not there primarily to run a business. The universities should be places where you have intellectual freedom to investigate any aspect of the physical and biological and natural world that is worthy of being investigated. And of course, when now policies that money is allocated to various funding authorities, and the politicians have a big say in this. They say, no, what we want is to push more people towards solar energy. Well, of course, solar energy, we need to harness it. But it doesn't necessarily follow that by putting everybody in droves into solar energy, that the most significant breakthrough is going to come from having a sort of army of people devoted to that. You allow individuals to have free thinking and sorting out, you know, when Faraday discovered electromagnetic induction, which gives us all this electricity, and has done so ever since 1831. At that time, there was a committee set up by the British government to look into improvements in street lighting. And they had an engineer, they had a ceramicist, they had a mathematician, and a physicist, and a chemist, who were looking at ways of improving the efficiency. You would have got 5% more illumination and less gas being used and so forth. But in the basement of the Royal Institution, you have a man who is looking at the relation between electricity and magnetism. And he discovers electromagnetic induction, which gives you the dynamo, the turbine, and the generation of continuous electricity. So that's an example, you see. Why do you ask? Have you a political...
Well, I agree with you completely, and I find very frustrated the way a lot of governments are going. Where I come from in Canada, the National Research Council is being retooled as a sort of, I don't know, towards the business end.
That's right.
They want ideas from pure research to be easily transferred into something patentable. And I feel this violates what you're saying, what universities should be, what research should be, and I think this talk you're giving is something that all policy makers should be aware of if they would listen to it.
Yeah, well, I mean, some did listen to it. Whether they've acted upon it's another matter, of course. But I only wish they did. I've given this talk in Japan and also in Germany and in China too. And in some instances, I think people do take note of it, but whether they act on it is another matter, you see.
Okay, I think we might end there. Hopefully Professor Sir Meurig Thomas will stay around. We have some snacks and drinks outside the lecture theatre. If you do want to become part of the committee of the Science Society, as I mentioned earlier, stay here for about 20 minutes or so. We'll hold additional elections. And finally, I'd like to thank everyone who's come this term, especially Professor Sir John Meurig Thomas and all our speakers, and hope to see you next term.
Good. Thank you. I don't want to miss my memory stick.
Thank you so much.
Yeah.